Welcome to the pre-recording of lecture 33, scheduled for Monday, 3 April. So this lecture concludes a chapter on pipelining and synchronized computing, but in essence it's also a lecture on GPU acceleration. We have essentially not really considered when we launch a kernel, we must specify the number of threads per block. This is essentially the first half of this lecture. I will also say something about the use of registers, how they can be used to have additional instructions and provide more opportunities for latency hiding, as we have covered earlier. And in the third part of this lecture, so it's already 2023, I will say something about Tensor cores, which were introduced in the Volta architecture in 2017. So in a way, the third part is again rather getting technical, but it's also making the transitions to the applications aspects. So the revolution that we have seen in teraflop computing at the chip level has led to many interesting applications in science and in engineering. All right, so to make this slide self-contained, so we are here addressing essentially personal supercomputing. So I checked this morning my notes from 2006. Then the computer that we were using, the supercomputer we had access to in the National Center of Supercomputing Applications in University of Illinois at Urbana-Champaign, the theoretical peak performance was 2 teraflop, and that computer was somewhere number 99 at some point in the top 500 of supercomputers. Currently we have graphics cards, so Pascal is capable of 4 teraflop the peak performance, 64-bit precision. So 2016 was about 2006 was about 17 years ago. Depending on your age, this might be quite a long time, but still it is remarkable the performance increases that has been realized in a little more than a decade. So the programming model is far more refined than we started with in the beginning of the course with message passing and then later with multi-threading. Here we deal with instruction level parallelism. So a thread is running in warps, and warps of threads are executed in blocks of threads. To keep the GPU fully occupied, that's necessary for teraflop performance, and that is actually our main concern also a little bit of this lecture. When we launch kernels, we are doing a kind of synchronized computing. It is the CPU, the host, that will keep the beat of how the computations are orchestrated. In each kernel launch, we must decide how large the threads will be, how large the grids will be, the dimensions of each grid, 2-dimensional, 1-dimensional, 3-dimensional, and we must decide on the number of threads in each block. Also, we can verify in each, and there are profiling tools that will help us for this, how many registers that are used in each function, and we can compute how many threads we can possibly launch. So we will get to the notion of performance cliff. So the software development kit provides some tools for this. There is an addition of the compiler. There is the profiling, the visual profiling that is part of the tool set. So in this course, this is an introduction course, and we are actually very happy when we get something meaningful that runs correctly. But if you really are interested in using the best on developing the best types of software, so once you have correctness, you should be very concerned with performance. Speaking of performance, Tensor cores, not Terra cores, Tensor cores are now capable of accomplishing hundreds of, or at least double digits of peak teraflop performance, also with 64-bit double precision. Okay, what are the resources that we have? So if you look at the device query of your GPU, so here this lecture is entirely CUDA centric for NVIDIA GPUs, although a lot should be transferable to other types of GPUs. So we have the number of threads per block. We have the number of blocks that any streaming multiprocessor can handle. And you see that among the several compute capabilities, among the several generations of GPUs, that the warp size, so the warp is the unit of 32 threads that execute simultaneously, that has remained constant. What has increased is the number of resident warps per streaming multiprocessor. So and that's a good thing. That helps us with the latency hiding. So this is from CUDA C programming guide along various generations of GPUs, going from a laptop that had GeForce 900 400M going to the Pascal P100. So what does this imply for us? So the scalable programming model means that the threads are executed in blocks, and blocks are partitioned, and they are actually, the thread slots are the available thread slots depend on how many blocks of threads that you can schedule. So either we have many thread blocks with few threads, or we have few threads block of many threads. So you can ask yourself, how should you divide your configuration parameters when you will schedule your, when you will launch your threads. The overall goal is to keep multiprocessors fully occupied. So let's look at one example over 3 different GPUs. So in essence, it's GPU dependent. So when you do an experimental study, you have the choice on your available thread slots to have how many warps per block you have. So here in this calculation we can have 48 blocks. If we consider 32 threads per block, we can have at most 8 blocks per streaming multiprocessor. So in order to have 8 blocks per streaming multiprocessor, we could have 192 threads per block, or 6 warps per block. And that is regardless of your subdivision of your, if you use, for example, a multidimensional grid computation, you actually get quite quickly to the 192. So it allows you to schedule 32 by 32 for one block, and then actually you have 1024 threads per block. But that will mean that you will not be able to schedule as many blocks per streaming multiprocessor as are possible. What is it on the next generation? Well, on the next generation, the Kepler architecture, we can have 2048. We have 2048 thread slots per streaming multiprocessor. If we divide the number of thread slots per warp size, then we can have at most 16 blocks per streaming multiprocessor. And this leads to 4 warps per block or 128 threads per block if we want to occupy the GPU fully. So one can see this as constraints, as guidance on how to partition. On the Pascal, which has also 2400 thread slots, but now the number of warps per block is actually, we can now have 32 blocks per streaming multiprocessor. So now we can have 64 threads per block or 2 warps per block. So in order to keep the GPU fully occupied, this gives us some bounds and some guidelines. So that's the first way how to interpret the resource limitations. So this is the main resource limitation being here the number of thread slots given taking into account the warp size. Okay, so the second category of resources are the number of registers that are available per streaming multiprocessors. So with the compute capability, so the very early and actually the not so strong graphics cards have compute capability 1, a little bit over 1. Pascal has compute capability 6, and you can see that there are 64,000 registers. The number of shared memory has also been increasing, but however, and this is actually to keep in mind, the number of threads has actually grown much faster than the number of available memory, shared memory. And the amount of the available memory, that will often also be extra constraint. So you can see the local, the constant memory has not grown in size. And constants are indeed for constants, and they should be limited in size. One mistake that we made in our earlier designs in polynomial evaluation and differentiation was to store the exponents in constant memory. In some sense, it made perfect sense at the time. Exponents remain constants, whereas the coefficients may vary. However, if you are solving larger and larger polynomial systems, you get into trouble with this constant memory. Okay, cache memory has also not actually increased all that much. So on the one hand, if you, because of the lower, because the shared memories, they actually act very much like registers, very fast access, you should, whenever possible, you should make use of shared memories. However, you constantly have to be aware that shared memory is a very limited resource, and if you are using too much of your shared memory, your compiler will typically warn you for that. That also will put a restriction on the number of threads that you can keep running. Okay, so here is what I tried to explain when the previous slide was up. So registers are used for local variables. Shared memories are actually used for arrays, for relatively short arrays. So you can accommodate more blocks of threads if you have few registers. But if you occupy too many registers, then or too many shared memories, then actually you can have fewer blocks. In some sense, there is often a trade-off. You can trade shared memory with registers. So this is, for example, particularly useful in the context of multiple double arithmetic. Instead of using 8 shared memories of 8 long, you can work with 8 registers, or the other way around. So here is an example. Suppose that a kernel uses 21 registers and we are having 16 by 16 thread blocks. So how many threads can you actually run? So we can calculate how many registers that each block will use. So every thread uses 21 registers. We have 16 times 16 times threads in a block. So we are using 5,000 registers. And how many registers do we have in every streaming multiprocessor? We have 32,000 registers. So this implies that we can run only at any given point 6 blocks. And the streaming multiprocessor can actually hold 8. So instead of 6. So all the considerations that we had previously, we have to take into account the number of registers used by a kernel. So this also implies the limitation on the parallelism. So we can hold at most 1,536 threads per streaming multiprocessor, which is actually a lot, by the way. But this gives kind of an indication about the range. So we have the number of available cores. So streaming multiprocessor here has a number of cores which is in the less than the double digits, but you have to schedule many more threads because of latency hiding, but there's also an upper limit over there. Now, here is kind of the unexpected behavior. Suppose that you would be thinking, hey, I'm going to introduce an extra local variable in my code, and that will lead to savings, an extra register, so by and also saving of an operation, perhaps, or extra latency. But then you figure out that all of a sudden the performance dramatically drops, and this is when things get really disappointing. You spend your time thinking of what would be an optimization, and it actually turns out the opposite. Here is the scenario. So instead of 21, you use 22 registers. Now you are you're using many more, and it actually matters because instead of 6 blocks, you can only hold 5 blocks per streaming multiprocessors. And that significantly reduces the number of threads that you can keep resident on one streaming multiprocessor. So making a rather innocent change, which one could have considered as an optimization, leads to a 17% reduction in the parallelism. And that is a performance cliff. Okay, how could you discover whether this happens? So there is the CUDA GPU occupancy calculator that you can find in the tools. So in a way, this is CUDA centric, and I'm going to flash several slides rather in very quick succession now. What the purpose of this lecture is that you are strongly invited to explore when you install the software development kit what is in there. So here you see what is there with the CUDA occupancy calculator. I should actually have a live demonstration, but what this slide allows you to do, it has these parameters in there, and you can actually by doing the computations that were illustrated on the previous slide, you can come up with what the bottlenecks are essentially in the performance analysis. So then there is also the dynamic allocation. As you are running code, you can run also the performance analyzer. So there is the compute profiler, and it's a visual tool. It's a graphical user interface, and you can run it if you run it remotely. There is this SSH-X, which will essentially work if you're working also on another Unix terminal. And there are tools for X Windows forwarding both on Windows and most likely also on Mac. So to launch this remotely, so what will happen after a run is that it will indicate which kernels have been most active during the run. And this gives an indication. So in some sense, I mentioned the optimizations. Once you have something that is correct and running, you may be wondering what could be improved. Well, the compute profiler is actually a very good point to start. So this will say which kernels require attention. Here is the summary. And I would like to indicate we had the instruction per byte ratio. What we defined in the course was the compute per global memory access. So here it states that the limiting factor is actually the instruction per byte ratio. That is here for this type of kernel 10. So we do 10 instructions per byte. So you can see what also is the memory bandwidth. So we have a throughput of 10. And actually the peak memory bandwidth, so here still expressed in gigabytes per second, is 144. So you see that compared to the CPU, we're doing quite well, but compared to the peak memory, global memory bandwidth of the GPU, we actually are doing not so well. We did one matrix multiplication. At some levels, so we have an achieved occupancy of 0.67, and the theoretical occupancy is also 0.67. So it's not all that bad. So it is also an analysis of the throughput for this kernel. The memory access to the global memory, the use of the caches. And again, at the bottom line, there is the peak global throughput, which that stands at 144. Not that bad, we get at 23. That's the largest numbers that we kind of see, but not at the peak. Which is probably okay, because this is essentially still a memory intensive, more a compute bound than a memory bound computation. So we computed, so here is actually something that is not that good. So this is the instructions per cycle. So we had now the IPC. So I will go that also. So we had in some sense the concepts that we introduced in previous lectures are very good here. So we talked about bank conflicts. So here there are no bank conflicts. The thread divergence. So here you see the control float divergence. So there is no branch divergence, also 0. So in a way, the report card looks very good, which you would expect from something that is coming with the software development kit, the matrix multiplication kernel. Okay, so we are here now at the level where it computes the number of registers per thread. As a programmer, you can of course compute the number of local variables that you are using, but there are also hidden uses. So you have loop counters that you may not take into account. Here you see how many registers that are really being used. And it also actually tells you that your occupancy is actually not yet ideal. So you're at 66% of your potential occupancy. So you could still do more. So the number of active blocks per streaming multiprocessor was only 1 instead of 8. So the block size is actually, the 32 by 32 is actually quite bad. So 1024 threads per block. So we are actually at the case where the configuration parameters were actually not that good. And that's actually the invitation for experimentation. Run this again and see what the compute profiler comes up with if you have other configuration parameters. So there are some terms that some were somehow may have seen rather alien. So the instruction throughput. Often warps are being prevented from execution because they are accessing data. So they are waiting for accessing global memory. And data prefetching provides extra independent instructions. So here is the pattern. So we looked at actual code, which was kind of scary at times. But here you see the prefetching in registers. So we go from global memory into registers, and then from registers into shared memory. And that may seem completely far-fetched, to use the fetch word, so it's far-fetched. But if you think about adding extra instructions so that other threads could execute while other threads are waiting, then this actually makes sense. So the traditional hierarchy is global memory, shared memory, registers, but you can also use registers in between global memory and shared memory. This is of course prevented. This is of course that you are not now using too many threads in a block, or that the registers that you are using anyway during your processing of a current tile are actually already used before. So in some sense it looks far-fetched again, but with the intent of having more parallelism and latency hiding, it could be quite a good move. Okay, so we have the number of instructions per clock cycle. So many more is actually now better. So you see the number of instructions can be done per clock cycle. Remember that very early on in the course we had the performance metrics of floating point instructions per second. Here you see that you have the number of cycles per second, so the clock cycles, and that actually a GPU can actually do many operations per clock cycle. So the kind of instructions per cycle that you can do if all the instructions are lined up is more than one instruction per second. So I was executing on a C2050, which was still on the kind of low end for floating point operations, so somehow between 1 and 2. So you see that you get 32 floating point instructions per clock cycle. You also see the built-in functions. So the CUDA mathematical library also has support for the most commonly used functions, such as square root. We had our own square root, the logarithm, the exponential sign, and cosine. Okay, so I will end with loop enrolling, and the bottom line is actually, why do we essentially never really, as regular programmers, think much about loop enrolling? Because compilers with the optimization flag do this automatically. But when you think instruction level as a programmer, you may actually worry about this. So if you count the instructions here, you can trade in. So this is the point of this slide again, why loop enrolling is important. In also rummaging to my files earlier this morning, I was looking at the syllabus of a course, that the earliest versions of the course by Professor Floyd Hansen. Loop enrolling was actually a prominent topic on the syllabus at the time. So in some sense, if you do not consider GPUs, it's a topic that is kind of faded away. With the original, so GPUs have the benefit to bring us again closer to the hardware. You can see with this example, if you carefully examine all the instructions that you are doing, only 2 of them are floating point. And what you're doing with loop enrolling, you are having fewer of those because you have many more instructions within a loop. So what loop enrolling essentially does, it is going to essentially, if your total number of steps is, say, a multiple of 8, then instead of having 1 instruction in a loop, you can have 8 instructions in the loop. And in some sense, you do some binary expansion. You could, in the very extreme, you do a binary expansion of the number m, and you write the number of instructions. You have one big block that schedules all the multiples, say, of 8. Then you have the multiples of 4, then the multiples of 2, and then the last instruction. So you can go very far with this if you want to really have good performance. Okay, I'm halfway through this recording. This would normally have been the end of the lecture, so I can deliver this faster and faster. Let me transition into the applications, but also transition into the more modern era of GPU computing. My most recent GPU that I have is a Volta, and I purchased this in 2019 via Microway. The Volta was bringing an enormous increase in performance with Tensor cores. So here is a picture that I stole from the Volta architecture white paper. So every streaming multiprocessor has 8 Tensor cores. The Volta that I have has 80 streaming multiprocessors, so we have 640 Tensor cores in total. And the Tensor cores give you mixed precision of 128 teraflops. So this is double, or actually triple digit teraflops. What is important is, again, that if you are finally attuned to your application, and I will give applications. My applications are polynomial system solving and running Newton's method. But what you do is you do convolutions when you evaluate a power series, and you do linear algebra when you are computing the updates. So if you can cover convolutions and matrix operations, you can cover almost all applications. The part of the Volta advertisement is, and the technical literature is actually always dedicated to the applications that have been made possible because of this increased performance. So what I will do in the next slides, in the remaining 5 to 10 minutes, is scroll through some screenshots. Here is what I copied from the Volta versus the Ampere. So the Volta is capable of also doing 64-bit tensor core, but then actually you are multiplying a 2x4 with a 2x4 with a 4x2, so you get a 2x2 matrix. So in some sense one needs to think about at a really fine grain level, but again we have 604 of those tensor cores. So again, twice 640 is again 1280. So there is power in the many. Tensor cores became more and more important in the next generation. So the Ampere gave another increase, so better throughput. And if you look to the Hopper, the latest architecture, which I dream to acquire in the near future, hopefully still this calendar year, there you see that the throughput is even higher. So the performance and life in the future will look brighter and brighter. Okay, so I will end with an excursion into the CUDA development kit. Here's still a picture that I stole from a tutorial. So Volta came out in 2017. In 2019 at the big supercomputing conference, there was a tutorial about this. I stole this picture from it. So what the tensor cores can do is they do this mixed precision matrix multiplication. So it's more than a matrix multiplication. So you have the matrix multiplication and also the addition of another matrix. And it does actually do more. But you see the picture of the tensor cores. So here now we are looking at a 4x4 matrix. Again, you should see this multiplied by many, many tensor cores, hundreds of them. And here's some, again, what I learned from looking at the programming guide, which is actually a recommended reading. So even if you do not have an advanced GPU at your desk, it's worth looking at, and I will say in a minute why it's so funny. So the programming guide, so you can do this for compute capability 7 and higher, which is Volta. So Pascal is compute capability 6. Double precision is supported for compute capability 8. We talked about thread divergence. You better don't go overboard with this thread divergence here. You can still have branchings, but you still must ensure that all threads within a warp execute the same code. Otherwise, and it's very plain, it's going to hang. So, and I had cases on where I have newer code that I run on my older GPUs, and it simply does not terminate, get stuck. So there is the notion of fragments. So this is C++, so it's templated type. So you can describe the which matrix that are held, the A, the B, or the accumulator. You can define the shape. And also important, whether the matrix is stored row-wise or column-wise. So we address this when we consider the A and the B matrices. So I looked at, I scrolled through the CUDA C++ programming guide, recent edition. I discovered that the latest CUDA versions have actually facilities for reduction. So in a previous lecture, we carefully went through a technical report of Harris about how to write good kernels for for the prefix sum. Well, actually, if you really have to do this on the latest GPUs, please apply the tools that are available there. So that doesn't mean that much of what we have covered is obsolete by now. Far from it. You will get a greater appreciation of what is available. The other thing that I find typically funny, so the APIs, the modern APIs can actually do a hello world now, hello CUDA. So you can write a very short GPU program that actually have the threads write, hello, I'm doing this. This was new to me, and it's tucked away right in the middle, page 200 somewhere of a 220 of a almost 500 page programming guide. So this is also, if my lectures are kind of piled up. Also the CUDA programming guide, the most simplest constructions you find kind of in the middle. So that is the fun part to end with. And of course it works. So I have a Volta computer at home, which I put into the quarantine at the COVID-19 seclusion, and actually the most of that fall semester when I had a sabbatical. What made it really worthwhile was that I had this computer at home with me. I was doing learning a lot. Here is on the simple side of things, so it contains a lot of interesting examples, and again the Pascal GPU that we have all access to enrolled in this course has a very extensive samples kit. Here you see a running, and it clocks at 49 teraflops performance. So this is mixed precision. So the advertised is 125 teraflops, but this goes to close to 50 teraflops. Again, the supercomputers that we were using when I was beginning to teach these courses had single digits teraflops peak performance. And this was then, we could only use, of course, only a limited portion of this computer. Now actually you have a graphics card that is all for yourself, and that has teraflop performance. Okay, so what did it do? So here is the last slide. So it does a warp matrix multiply and accumulate. I had to look up what is the CTA. So that's not the Chicago Transit Authority, but it is a cooperative thread array. So what is very beneficial, what we have gone through this course, is already we understand the benefit of storing row-wise or column-wise. So in the fragments, one can define this, whether it is row major or column major. We also went in great details over the tiling. So tiling will again be addressed in the application side when we look at some multi-core libraries, multitasks, linear algebra again. But here you see how the division works. So these are tiles of 128 by 128 running 8 warps. So the size of these matrices are already quite considerable, 4096. Okay, so this was a very brief introduction into Tensor course, too brief. So in this lecture on performance considerations, I was still very much following the first edition of the book on programming massively parallel processors. A lot comes from earlier editions of the CUDA programming guide. Now, every computer comes with a graphics card, and your operating system should be capable, should tell you which it is. And at that point, you can Google around to see the specifications of the vendor. That should detail you if it's an NVIDIA one, then of course you must install the NVIDIA programming toolkits at the end of this course. Well, already you must have installed it. And then experiment how you can experience the resource limitations, be it the resource limitations of the number of available thread slots or with the available registers blocks. So these exercises will essentially no longer be collected because they came in the first time when I was teaching this at the very end of the course. But they can be made quantifiable, and they are definitely worthwhile doing. So I hope that this lecture was interesting. In the next last part of this course, we go more towards applications.